Hey everyone, my name is Shrey Gupta, and I'll be presenting on leveraging machine learning to improve robot motion planning in unknown environments. So to start off, I want to cover what exactly multi-robot systems are, and then we'll build upon this topic. So multi-robot systems are preferred in various scenarios over singular agent robots, specifically because they can take a more complicated task and split it up into subtasks and tackle these subtasks individually. And together they can work to provide a viable venue to enhance automation. And this allows these robots to provide robustness and resilience to the more complicated problems that we deal with today. They have many applications such as search and rescue, exploration, and logistics. So to give a quick example of what a search and rescue application can look like, suppose there's some damaged underwater rig, you can deploy a multi-robot system of underwater robots, and they can split up this part of the rig into several sections and individually compare information and eventually create a whole picture of what this rig looks like and where the damages have occurred. So now I'd like to go into what multi-robot motion planning is. So this is a fundamental component to enhance the autonomy of robots. So what this means is that there's going to be several robots in a grid-like system or in some sort of environment, a map. And what we're doing is taking each robot and getting it from point A to point B while avoiding collisions with the obstacles and each other. So this is significantly more challenging than singular agent planning because they have to take into account the other robots that are moving alongside them. So now I'll be touching on what was required to make the base framework of this project. So the base framework included adding the aspect of unknown environments. So unknown environments is the unique aspect of the project, the base framework part of the project. And this also makes motion planning more challenging because robots have a limited view of the environment around them, and they're equipped with simulated sensors to collect information about the environment around them. And as these robots move through the environment, they incrementally build a view of the map as these robots are able to communicate with each other and collectively build some understanding of their surroundings. So this is a quick demo of what this looks like. If you see the red obstacles, those are the ones that have been discovered, and the gray ones are the ones that have not been discovered. So as you can see, the robots are moving through the environment and discovering more and more obstacles, and that is allowing them to plan better to reach their goals. So the current proposed approach of what this looks like is each robot is going to sense using the sensing algorithm that is in place. And if any new information is found, then these robots will need to replan their motions to get to their final destinations. Once these new plans or paths have been found, these robots' current positions are updated to the new step, and then these robots are going to sense again in case any new information can be found in this new location. So this is how the cycle works to get to their final destination. So now I'd like to touch on the sensor implementation. So the whole point of the sensor implementation is to simulate what a sensor would look like if we were using physical robots, but this is a completely simulated project, so I had to come up with some sort of sensor implementation. So the way I did this is I would compute some of the cells in a given range, so in some radius around my robot, and then I would figure out which ones are free, which ones are occupied. So for the occupied cells, or the cells that have obstacles in them, I would draw a line from each of those cells to the robot. If they intersected with another occupied cell, then I knew I could not see that obstacle, and it wouldn't be an obstacle that would be updated in the incremental map. So this allowed me to simulate the sensor. So the planning algorithm that was in place is based on a conflict-based search, which is an extension of the tjSTAR algorithm, and it uses robot paths to reduce conflict. So like the conflicts that will occur and the intersections of these paths. So I added a cost function to this conflict-based search planner to incentivize safer exploration, so it'd be more accurate to the real world. So what I did is I made a high cost to planning motions to known obstacles, and I gave preference to areas that we like had familiarity with, so areas that have already been sensed, and there would be a higher penalty to move to unsensed areas. So the robot would prefer to move to areas that have been sensed, and it would stay away from obstacles. So now we're going to be getting into the FASTER framework and how I improved upon this base framework. So the problem is right now that heuristics and planners get stuck, and they can get stuck because they get in tricky scenarios where there's like narrow paths, or there's areas where like two robots are trying to go along the same small section of space, and they're often exploring the same environments over and over again. So machine learning is great at this because we can allow the robots to like overcome these tight scenarios, as well as learn about the environment around them that they're constantly going through. So the data that I implemented is agent goal and start positions. So it'll be like where the agents are going to start, where the agents want to end up, the average distance, so how many steps it took for the robots to get there, and the replanning count, or how many times the robots need to replan after sensing new information. And what I wanted to predict is the total time. So with these tested machine learning techniques, this is the data that I got for a singular agent. And as you can tell, for random forests, there is a bit of a low tolerance level. So this tolerance level indicates like how many data points are we correctly predicting within 1 second. And for the gradient boosting, we have the highest of around like 93%, and neural networks is similar to the random forest, but performs slightly better, closer to like the high 80s, so around 88%. And here are the error graphs. So this provided a little bit more insight into which algorithms have the lowest error. As you can tell, the neural networks have a pretty skewed right error, which gave a little bit more insight over why it might be worse over random forests. Additionally, the XGB seems to have a higher error percentage, around 20, and random forest has the highest error, or lowest error, around 10%. So we have the obstacle density of two agents. So this is a little bit more data I want to collect. So I varied the obstacle density of the maps, which means how many obstacles are there per the 32 by 32 grid that I inputted. So a 5% obstacle density would mean like 5% of those squares are covered in obstacles. And I varied it by increments of 5%. And for the 5 and 10% values, you can see that the obstacle density or the tolerance levels for these obstacle densities are relatively high, and around 15 and 20% they start to fall off. So in the future, I want to do a little bit more research into why this occurs and how we can create more parameterized maps to solve the random nature of the maps that I'm creating right now. And this might improve the obstacle density for 15 and 20%. So while this project did not reach its initial goal, which was to create a heuristic that could predict the planning time to move to region. But what it did do is that it proved that machine learning has some application to multi-robot systems, which is incredibly important because it provides like a stepping stone for future machine learning and multi-robot system research. And hopefully it can create the framework that I intended to make, which was allowing for robots to predict their runtime for different cells around them. And then eventually we can guide these robots to these lower runtime regions and create some sort of heuristic for accomplishing this task. And as I touched on earlier, I also want to create more parameterized maps, which can include using the breadth first search algorithm, Kruskal's algorithm, and a variety of others that have been used in areas such as game development to create better maps that the machine learning models can learn better from. And this might also be applicable to the scenarios that these robots would be going into, because they typically aren't going to be encountering obstacles which are completely randomized across some sort of grid system. So these are the 3 goals that I want to accomplish, and I hope you learned something from my project. Thank you.